we're going to talk about elastic collisions. Uh, as with any collision, momentum is conserved. Okay, so momentum's conserved in elastic collisions, just like in inelastic collisions and perfectly inelastic collisions. Momentum is conserved. Momentum's conserved in all the collisions. Uh, what's different about an elastic collision is energy is conserved, okay, as well. There's conserved energy as opposed to lost energy uh, in the inelastic collisions. Uh, the there's no transfer of energy into heat, so we can use a conservation of energy without any work out of the system or energy losses uh, coming into play. So uh, the best way to understand this is to kind of teach how to solve these problems, and let's show a picture of two objects that are moving towards each other. So we've got a red ball and a green ball, and they're going to be moving towards each other. So you got a red ball moving with a velocity this way, and you've got a green ball moving with a velocity this way. Okay, so let's give some magnitudes for mass and velocity for both of these things, and we'll get ready to solve it. So here we go. So the red ball we're going to say is moving at 8 meters per second, and it's 2 kilograms. The green ball is moving at 5 meters per second with a mass of 3 kilograms. But notice the green ball is moving in the opposite direction, so let's make him negative. He's negative 5 meters per second. And so we know that velocity is conserved. What we want to know is what is the velocity after the collision. So what do they actually look like after the collision? So they're going to come together and collide with each other, and then they're going to ricochet off. And let's look at what we're talking about. Okay, so I have our simulator here, courtesy of the University of Colorado, uh, with their simulations. Uh, and you can see the velocity vectors. You've got the 3 kilogram object, green one, and the 2 kilogram red one. And the red one's moving at 8, the green one's moving at 5. So if we play this out, they're going to hit, and notice that their velocities go in opposite directions. They're going to hit and ricochet off each other. And we want to know what those velocities are. Well, the simulator is telling us these are the velocities. So let's see how the simulator comes up with that. So after the collision, now the red ball is going this way, and the green ball is going in this direction. And we want to know what this velocity is. This velocity is in question, and this velocity is in question. Okay. Yeah, you guys know it because you looked at the simulator, but what if we didn't look at the simulator and we needed to figure it out on our own? Again, this is still a 2 kilogram ball, and some of the other things we need to label is, well, this is initial, and this is final velocity of the red ball. Let's call it R for red, and let's call this one R for red. Okay. You don't have the luxury of having colored pens for your, on your test, so you're going to have to distinguish it some other way. So let's call this green, and this is final velocity of the green. And we're trying to figure out these two velocities. The mass hasn't changed. Okay, mass is still 2 kilograms for both of them. Okay, mass is still 2 kilograms for both of them. This is, I'm sorry, 2 kilograms for the red one and 3 kilograms for the green one. Mass hasn't changed for both of them, is what I meant to say. So, one thing we're going to need to do is realize that momentum is conserved. So that's the first step. Let's go through the momentum and say, okay, that's conserved, so my initial momentum has to equal my final momentum. P initial has to equal P final. So, what is the initial momentum made up of? Well, that's the initial mass of the red ball times the velocity of the red ball initial plus the mass of the green ball times the velocity of the green ball initial. And that has to equal the mass of the red ball times the velocity of the red ball final and the mass of the green ball times the velocity of the green ball final. And there we go. So let's start plugging in numbers for this. If we look back, we can see that the velocity initial of the red ball is 8, and the mass is 2, plus the mass of the green ball is 3, and the velocity is -5. That is equal to the mass of the red ball, still 2, velocity of the red ball, I don't know, final. And this is not a situation where the red ball and the green ball have equal velocities as it was when we had perfectly inelastic collisions, because now they're separating. Okay, so we can't say that they're equal and use that simplified equation. So we've got 3 times V green final. So we have an equation with 2 unknowns. Okay, we have an equation with 2 unknowns. We need another equation. And where is that going to come from? It's going to come from our energy, our conservation of energy. Energy initial must equal the energy final. That is for an elastic collision. So let's go ahead and simplify this real quick and come up with a nice equation, and we will then figure out what our energies look like. Okay, so we've cleaned up this equation and gotten it down to 1 equals 2 final velocity of the red ball plus 3 times final velocity of the green ball. Now we're going to look at our energy side. And with the initial energy, we have a lot of things here. We have the initial energy of the red ball, the initial energy of the green ball. Okay, and so this is a little different than the way we dealt with energy in our last chapter, where it was just one object. We've got 2 objects here with energy. Okay, so they get added in together for the initial energy, and the same thing happens for the final side. Okay, now what are the energies that make up the red ball? We don't have to worry about potential energy, because we can assume that this thing has an energy grade line that is, let's make that a little less thick, but we can assume that our potential energy line here has a height of 0, so they both have 0 potential energy. Okay, we can make that assumption, and we don't need to worry about potential energy because we're going to assume they're at the same level. So we only have to deal with kinetic energy. Okay, so we need the kinetic energy initial of the red ball plus the kinetic energy initial of the green ball equal the kinetic energy final of the red ball and kinetic energy final of the green ball. Okay, and then we just take these equations and or these and expand them out into their mv squared over 2 equations. This expands to the mass. I should have r in there for the red ball times velocity initial of the red ball squared over 2. Don't forget to square it. And then this would expand out to mg v initial g squared over 2. The next one, mass of the red v final of the red squared over 2. And last, mass of the green velocity final of the green squared over 2. And then we'll just put numbers in here and see what equation we get through energy. Plug in numbers. For the first one, we have 2 times 8 squared over 2. The second one, we have 3 for the mass. Initial velocity is -5, and that's -5. And last one, mass of the red ball is still 2. We don't know VFR squared over 2. And again, we don't know the velocity final of the green. So we've got another equation with 2 unknowns. Luckily, they're the same unknowns. V final of the red, V final of the red, V final of the green, V final of the green. So let's clean up this equation and see how we can plug one into the other. One of the ways I'm going to clean this up is I don't want to have decimals when I have a squared term here. So I'm going to multiply everything by 2. If I multiply everything by 2, it'll keep me from having decimals in my equation. So let's multiply everything by 2. And we'll have our final equation. That's what happens, and we'll add these two numbers together to get our final equation. Is there. So we need to combine these two equations, and I'm tired of writing the same, all the sub letters. So what I like to do here in the next step is just say, well, V RF, which is the same as VFR, which is equal to VFR. I just switched the way I lettered them over here. Let's make them equal to the letter X. Okay, let's make them equal to the letter X. So they're equal to X. Okay, and the same thing for V final VGF, which is the same as VFG. Again, I just flipped the lettering. It doesn't matter. If you have it labeled the same way, that's good. Let's say those two are equal to y. So these are my x's, and these are my y's. So what do my two equations look like after I do that? They look like this. Okay, plugging in the x where x is supposed to go, and y for what y is. Now we're going to solve for x and y, but we have to do that through simultaneous solving. So let's pick one of these and rearrange them. The way I'm going to do simultaneous solving is through substitution. So I'm going to pick my equation over here because it's a little easier to work with, and we'll plug it in over into this equation. Subtract 3y over to the other side, and then we'll divide by 2 from both sides. So we have x equals 1 minus 3y over 2. So we take this entire thing, okay, we take this entire thing, and we're going to plug it in for x over here. So when I plug this in, we've got 203 equals 2 times the entire term of 1 minus 3y over 2, the whole thing squared, plus 3y squared. So we'll start solving for y. And when we square that entire term, 1 squared is 1. We've got a negative 3y times 1 plus a negative 3 times 1. It's going to give us negative 6y plus 9y squared. You can FOIL this out if you need to FOIL it out. FOIL the top, square the bottom. Excuse me, this shouldn't be 2, this should be 4. Continuing out, we're going to get 203 equals, this whole term is going to be 1 minus 6y plus 9y squared over 2 when you multiply through by the 2. And I've got a situation here where I've got a 2 down here, so I'm going to multiply everything by a factor of 2 so that I can start combining like terms. It's just a algebra move that allows us to, helps make it easier to combine like terms. Again, I multiplied everything by 2, so I got 406. That got rid of the 2 down here on the denominator, leaving us with this term, this whole term, and got to multiply this term by 2 also, so I get 6y squared. And now I can start combining like terms and set it equal to 0. Combining your y squared terms, you get positive 15y. Subtract the 406 over, and you get a negative 405 when you combine it with the positive 1 and negative 6y. So here we have a quadratic formula, and a quadratic, and we're going to use the quadratic formula to solve for it, because I'm not going to go through and try and find common denominators or common factors to try and figure out what y is equal to. I'm just going to plug it into the quadratic formula and solve for y. And when you plug that into the quadratic formula, I'm not going to show you that here because you should know how to do that. You're going to get y equal to 5.4 or negative 5. And you'll know you've done this right if if this term, the negative 5 here, comes out, because if you look back, you'll see that initially that y was in reference to the green ball, and the green ball was initially going at negative 5. So you're going to come up with the same velocity that you had initially for one of the solutions to this problem. And the same thing will work if, instead of plugging the x in, you did with, you isolated y and plugged that in for y. Doesn't matter which way you skin it, you're going to find a term. So in the case of the green ball, you're going to get its initial velocity. If you'd done it the other way with the red ball, you would get the red ball's initial velocity when you solved through. So that leads us to understanding that the choice that we're going to make between the two is going to be the 5.4. How do we know that? Well, we know we got an elastic collision, and we know it's not going to have the same velocity. After that thing hits, its velocity is going to change, and it's going to change in a positive direction. So we know we can pick this for our final velocity of the green ball is equal to 5.4. Okay, final velocity of the green ball is 5.4 meters per second. And to find the velocity of the red ball, I can take this and plug it in to this equation and solve for the red ball. Plugging it in, and you'd get negative 7.6 for x, so that tells me that the velocity final of the red ball, which is x, is equal to negative 7.6 meters per second. And one thing of note, like I had said before with this negative 5 being the initial velocity of the green ball, if you want to double check yourself, plug this in for y, and you'd have negative 5 times negative 3 is positive 15, plus 1 is 16, divided by 2 would equal 8 for x. If you made this selection, so you would be saying that x is 8, which was the initial velocity of the red ball. So we can deduce that, uh, after the collision, they're not going to have the same exact velocities. So we know we've made the correct choice. The velocity final of the red ball is going to be negative 7.6. Velocity final of the green ball is 5.4. And just for the heck of it, let's go back to our simulator and see if we're right. And we're back to the simulator, and we can see the velocity of the red ball, negative 7.6, velocity of the green ball, 5.4. So taking away from all this, remember with the elastic collisions, momentum's conserved and energy is conserved. And one of the tricks you need to use is that the potential energy is 0. Use potential energy of 0 for your energy equation when you're balancing that out.